Hey physics students, this is Mr. Gloria coming at you again. How are y'all doing today? Hey, I'd like to do a second part of this free fall information. We did the first part of the video, and we talked about dropping objects, what free fall was, etc. Now in this video, we'd like to project an object upward and then allow it to come back down. So we're going to have a little bit more complicated type of a motion. It's going to be one complete free fall motion up and down. I want to first look at the vectors involved, a motion map, and look at the motion graphs for this type of motion. Secondly, I'd like to then do a LogRPro video analysis where we're looking at the graphs and some real data and some real graphs. And finally, I'd like to work a few practice problems with this type of motion, how fast, how far, etc. That's the plan. Okay, so let's kind of get started here. So let's first look at some of the vectors, motion map, motion graphs. We want to basically project an object straight up and allow it to come back down. So let's maybe make a drawing here first. So in this case, why don't we just have it come directly off the ground. So we've got to get that object off the ground, we've got to project it then with some sort of initial velocity, v sub I. And over time, that velocity is going to get less and less. And there's going to be then a top or an apex, which we call the top of the trajectory, that this velocity here at the apex is 0. So what I've drawn here are velocity vectors. Now, why is our velocity decreasing with respect to time? Well, we have the gravity pulling down on it, and we can show that gravity then with a vector. And that gravity is going to act, at least close to the Earth's surface, it's going to act at little g, negative 9.8 meters per second squared, throughout this whole upward motion. And so this gravity is going to stay constant here, negative 9.8, at least on our planet. And then again, that's a little g. We call that the acceleration due to gravity. Now, on the way back down, then we're going to have, assuming we have no air resistance, which is what we're neglecting with free fall, then our velocity vectors then will be symmetric. And so, for example, it's going to hit the ground with the same velocity, except it's just now a downward motion. When we projected it up, it was an upward motion. So these velocity vectors on the way up are positive. They're going to start off large and get smaller and smaller. And then there'll be then a point here, the apex we call it, that the velocity is 0. And then our velocities are negative then on the way back down. Again, the speeds are going to really be the same. We just have a directional difference with going up and coming back down. So that really represents our velocity, our acceleration vectors. This acceleration vector is going to stay constant throughout the entire motion, up and down. Well, so in terms of like a ticker tape, what would we see? Well, a ticker tape, basically, if we attach it to the object, that object's going to start off really fast initially, and then it's going to get slower and slower and finally going to stop. And those ticker tapes make dots, so the faster the object, then the wider space the dots are. Now, if we were talking about an object moving constant velocity, that spacing would be consistent. But because the object is slowing down, the dots are going to get narrower and more narrowly spaced with respect to time. And there's going to be then a point that, again, at the apex of that object is stopped. So we're going to stop that ticker tape right at that instant. Now, if we then have that object come down, we would see just the reversal with our ticker tape. So the ticker tape is really showing positional changes, and that corresponds kind of to our vector diagram there also. And the last set of diagrams I want to make then are our motion graphs. Okay, so now let's construct our motion maps. We have a position time, velocity time, acceleration time. And let's really just kind of start with our AT graph first. So our acceleration, we said, is due to gravity. The acceleration due to gravity. On the planet, it's going to be a unique value. We said, like, depending on the planet, it can be similar to Earth or greater or less. The Earth's gravity, then, acceleration due to gravity, is minus 9.8 meters per second per second. And as long as we're staying close to the Earth's surface, that value is going to stay constant. Well, a constant value on a graph is just a horizontal line. And in this case, and in these graphs, we really don't care, about it being real quantitative right now. We just want qualitative graphs. So what we're going to have for that complete motion is we're going to have a horizontal line. And let me actually put it into a color here so you can kind of see it a little bit better. So that horizontal line is going to be negative 9.8 meters per second per second. It's going to be in the fourth quadrant. It's going to be one complete horizontal line. Well, what about our VT graph? Well, we have to start off with some sort of a high velocity to project that object. So let's just say it's right here. And we know then it's going to come back down, and it's going, because of symmetry, it's going to land with that same speed. It's just going to be a downward direction. So at the end of that complete motion, we're going to have a point at the same speed, but just in the fourth quadrant. Now, we know then that this has got to this gives us a slope, because that slope is the acceleration or the gravity. Acceleration due to gravity. And there's one value here, one number. So that means that we have to just have one diagonal line. And we can connect our 2 points. We can connect our 2 points here then with one diagonal line, and that slope of that diagonal line again is going to be our acceleration, is going to be little g, which we see down here as this value here. So the velocity starts high as a positive number and gets smaller and smaller, and that's what we're seeing on our vector diagram, right? And there's going to be a point in time then that velocity will be 0, and that's where it crosses this axis right here. So this is basically motion up, and then we have motion down. Again, one diagonal, one slope. We start with a high positive velocity, and that velocity stays positive, but it gets smaller and smaller. That's what we're seeing here on our vectors. Then it becomes 0. That's our apex, and then the velocity then gets negative, but it starts small and grows and grows. Well, how would we translate all that then into a position time graph? Okay, I had to pause the video because I had a little bit of trouble with my dock camera, and we had just done the acceleration time graph and the velocity time graph, and we were getting ready to do the position time graph. I already have it kind of drawn out for you, but let me show you how we can get this kind of shape. We were talking about being at the reference point, so that reference point we can call x sub I then 0 and x sub f then 0. So we would start our 2 points here on our position time graph. Now we know then this apex point or velocity is 0, so we're going to have a horizontal tangent line right here. So our tangent lines then start positive at a fairly high value, but then they get less and less positive, get smaller and smaller as it then approaches 0. Then on the way back down, the tangent lines are going to be negative, because we have then increasing negative velocity. Starts positive, gets smaller and smaller, becomes then velocity of 0 at the apex. So we know then this is based on the square of time, so it has to be parabolic. And it's got one complete motion, one complete up and down motion, so it's one complete parabola. So that's kind of the parabolic shape that we get, and we can attach a line that really kind of bisects these graphs here. We have up and down, up and down, up and down. Now in terms of the acceleration time, it's one complete motion, one acceleration that doesn't change, and so we get then this horizontal line that looks like that. We have a diagonal line here, one complete diagonal, one slope to that one complete diagonal, which is the acceleration. We have one complete then parabola there. Okay students, that kind of completes the first chunk of the notes. So we looked at the vectors, velocity, acceleration, vectors. We looked at the ticker tape. We looked at the motion graphs, acceleration time, velocity time, position time graphs. Now I'm going to do a video analysis of an object being thrown up and allowing it to come back down, and we'll look at how the video analysis on LogaPro looks. Hey students, the goal of this segment of the video is to work a few physics free-fall problems with you. Let's kind of review our kinematic equations. So far we've got our CV equation. We really won't be dealing with or using this equation because free fall is an acceleration. We have our how far equation, or how fast. We've used those with previous PFA and some previous stuff we've been doing. We also have our timeless equation, which we've kind of combined our how far and how fast, and we factored out time. So in terms of free fall, we have these same equations. We're not going to change those at all. Often though, websites or textbooks might take that acceleration, that a that we have in these equations, the a, and we substitute little g for that. Little g again means the acceleration due to gravity. So we'll just substitute, then put in that little g, and that's telling us kind of that we're dealing with free fall sort of problems. Now, depending on what planet we're on, that little g is going to be a unique or different number. So for our planet, our little g is negative 9.8 meters per second per second. Most of the problems I've seen in terms of free fall deal with our planet. However, there are situations that you might be asked to find information about the moon or some other planet in our solar system. Typically you'll be given those little g's, although some problems, and I'll show you one of those, some problems you'll actually have to maybe solve for that little g. So why don't we get started, okay? Sounds good. Okay, students, so let's just say we're projecting an object upward. I just kind of drew a ball here, and we're projecting the ball upward with a velocity of 20 meters per second. We're starting at the ground. We're going to call that our reference point, and that ball's going to go up and up and up and up. And we said that velocity is going to decrease because we have the pull of gravity, and so we have an acceleration then that's downward. So our acceleration is directed downward, and if we do this problem on the Earth, then our little g again would be negative 9.8. And that, again, that's an acceleration meters per second per second. So the pull of gravity is pulling against this ball, but it has basically velocity upward. Gravity would be considered downward because it's directed downward. Our initial velocity is upward. So that velocity is going to get less and less over time. Finally, there'll be a point that object to stop, and we call that the apex. Our velocity there will be 0. So one of the questions we might ask is how far upward will the ball travel before it stops? Now notice here we don't really have time. So this is a perfect time maybe that we can use our combination or our timeless equation, vf squared vi squared plus 2g times our displacement. Now we know then that we're starting from the surface. We're calling that a reference point. We know our gravity is negative 9.8 meters per second per second. We know our initial velocity is 20, and what's kind of a key here to this problem is we know then at the apex that velocity will be 0. So we're going to call this final velocity, we're going to call it that apex velocity, and so we can put a 0 in there and just work out the mathematics. So we have to square that, put it on the other side, and then we want to solve for x sub f, which we're calling the apex, this apex final position. We end up getting then about 20.4 meters as a position above the ground. Now in some books or in some websites they might exchange y for x's because we're dealing with vertical motion. Not a big deal. So we're saying really that this object will go up 20.4 meters above the surface of the ground. The next thing we might want to answer then is how much time did it take for this motion to occur? The ball to go up until it then stopped at the apex. How much time did that take in seconds? Well, we can easily use our how fast equation. We know then that apex velocity would be 0. We're going to call that our final velocity. Our initial again was 20. Our g then is 9.8, and that's a negative. So we can solve that for time. We get around 2.04 seconds. So it's going to take slightly more than 2 seconds for that ball to travel on its way upward. Well, we might also want to look at somewhere in this trajectory at some other time. So for example, maybe we want to know how fast is the ball moving at 1.5 seconds. We know it's going to be stopped at 2.04 seconds, so we know it's going to be moving here with some velocity. So again, we could use the how fast equation, but now we're going to substitute 1.5 seconds in for time. So we have our initial velocity minus 9.8 meters per second times 1.5 seconds. we end up then getting about 5.3 meters per second for my velocity at that time. Alright, we might also want to know then how high or how far above the ground is the ball at that time, or how high is it at that time. Again, we can use our how, in this case we could use our how far equation, and again some textbooks or websites will put in a y instead of using x's. We started at the surface, we call that our reference point, so we have a VIT, so my initial velocity of the ball was 20 meters per second. My time was 1.5 seconds, plus 1/2 negative 9.8 meters per second times the square of time. We end up then getting about 18.975 meters. So the ball went up all the way up to 20.4 meters, 20.4 meters in 2.04 seconds. At 1.5 seconds, the ball's traveling at 5.3 meters per second, and it is up 18.975. So the ball would be somewhere maybe around here in its height or so. Now, sometimes they might ask you to find the total time up and down. Well, we know the time up is 2.04 seconds. So we have symmetry here, so the ball comes up, comes down, and if we neglect any sort of atmospheric conditions, air resistance, etc., the ball's going to have the same time up as it comes down. And so we can basically multiply that total time by 2, that time up by 2, and we can get our total time. We can multiply it by 2 or just add it to itself, we get 4.08 seconds total. So the ball would be in the air for that long. Finally, there might be some questions about how some free fall problems on other planets or moon or whatever, and all we have to do is, we're going to use these same equations, but we're just going to exchange the g. So if I'm dealing with the moon, I would put in negative 1.6 in for this, but everything else would be the same. So depending on what planet or what object they're asking you to work the problem on, you just use that g, and typically that g will you'll have to be given that. I have seen problems though where they might ask you to find the acceleration due to gravity for some planet given some information. So maybe we throw up this ball here on some other planet, and I don't know, maybe it takes 5 seconds for that ball to reach the apex. So our apex velocity again would be 0 right at the top, and that ball maybe again starts at 20 meters per second. So the question might be, what would be the acceleration due to gravity for a ball that takes 5 seconds to reach the apex if started with that velocity? Well, in this case, we know really 2 velocities, and we know the time, so we could use then our how fast equation. And so this apex velocity again would be 0. Our initial velocity is 20. And in this case, we're not sure what that g is, so that's going to be our unknown, but maybe it takes 5 seconds. And so we can put that 20 on the other side. Divide through by the 5. In this case, we get a g then of 4. We have meters per second per second. If it takes more time for that object to get up to its apex than it did on the Earth, so on the Earth it took, what did we say? On the Earth it took 2.04 seconds. So in this case, it takes more time, so we know the gravity is less than what it is on our planet. Now they might instead, they might tell you how far that object goes up on some planet before it stops, and instead of giving you, they might give you that information, and so instead of giving you time, they might give you how far up the ball goes before it stops. So I don't know, let's maybe just work one of those problems. So the ball goes up and up and up. Maybe again it starts off at 20 meters per second. That would be our initial velocity. And the ball then goes up and up and up. And I don't know, let's just say maybe it goes up 100 meters. And then before it stops. And so that apex velocity at 100 meters then would be 0. And maybe we'd like to figure out, they don't give us time here, and we'd like to figure out then what is the little g for this planet. And so again, with no time, it'd be nice then to use our timeless or combination equation. That final velocity we're calling the apex velocity, and that'll be 0. Our initial velocity again will be 20. We'll have to square that. And we're not sure what that acceleration is. We're calling that little g the acceleration due to gravity for this planet. And we know then the object goes up 100 meters. And it starts at the surface, which we're calling a reference point. Okay, so we have now this sort of calculation. We'll square the 20 and put it on the other side. So that's going to be minus 400 meters squared, seconds squared. That's going to equal then to 200. Meters times your g, and we're left then with the g of 2, in this case negative 2, and one of our meters cancels, so we're left with meters per second squared, or meters per second per second. So on this planet, if we could throw a ball at 20 meters per second, if it goes up 100 meters, then that would be our acceleration due to gravity, negative 2. Alright, those are some practice problems. I hope that helped. I also have some additional practice problems on the Summit or on the PFA. We'll talk to you later, kids. Bye.